This is section 1.7, linear inequalities and absolute value inequalities. The first thing we're going to discuss is what we mean by interval notation. So this is an example of something that's written in interval notation. We have a bracket and we have parentheses, and our numbers are in numerical order. What these numbers are is they represent the boundaries of the region we're talking about for our answer, because inequalities in general have infinite solutions, okay, because you have an entire range of solutions, the majority of the time, not every time. But the area we're interested in is between -4 and 3, so I'm going to put those numbers on my number line. And then a bracket, we put a bracket here. And this one has parentheses, so we use parentheses here. And then we shade between the two values. If you have an inequality, you will be graphing in some way and you will be shading in some way, okay? Now, what does this mean? Well, this bracket generally corresponds to either a less than or equal to or a greater than or equal to. Basically, the equal to is on there. It means that this endpoint is part of the solution. -4 is part of the solution to whatever this represents. The parentheses is corresponds with either greater than or less than. It's not equal to. Basically, in this case, our answer is from -4 inclusive all the way up to but not including 3. Okay, now you're going to have problems like this where they just ask you to translate interval notation into a graph, and they'll also ask you to rewrite the thing in what they call set builder notation. And what this looks like, it's the set of all x such that. The computer provides this part for you, and there's a closing brace on this side too. That's what the squiggly bracket's called. It's a brace. This says our answer is every x as long as, and we'll put some sort of condition right here. Well, the condition is that our x is between -4 inclusive and 3 not inclusive. This refers to one that has an equal to. This has without an equal to. So our answer in set builder notation is -4, which is my left-hand boundary, is less than or equal to, because it has a bracket, x is less than 3, in closed brace. This is what we're looking for. Now, one thing I do want to point out is there's an older notation that for some reason, some of the problems in my math lab still use. Okay, our new notation, I say new, it's been around for decades, but this is, we use the bracket and the parenthesis on the graph. That's the more standard way now. In the past, we used to use a closed-in circle or an open circle. Closed-in corresponds with a bracket, open circle corresponds to parentheses. This open circle we also use later whenever we are graphing in 2 dimensions, and we'll worry about that much later, but this does come up again. But just so you know, we normally use brackets and parentheses. Those are the best way to do it now. An older notation was a filled-in circle, open circle, and there are some problems in my math lab that use those. Okay, so let's do the same thing here, where we go from -infinity to 2. Now, you don't put the infinities on your graph. We only put numbers that we have. So I have a 2 here, okay? We don't write -infinity, we don't write positive infinity, but your negative infinity is on this side because all your negative numbers are over here. Positive infinity is this way. This is always your left-hand boundary, your right-hand boundary. Now, if we start at -infinity, there's no real left-hand boundary. We can't get to -infinity to include it. That's why infinities, whether positive or negative, they always get parentheses. The bracket would say that you could plug in -infinity, and we can't ever do that, okay? The 2 has a parenthesis, so this has parentheses. And then we would shade from -infinity up to 2 and not any further. If we were asked to write this in set builder notation, we would have the set of all x such that my x value needs to be in here. This has parentheses, so I'm going to use either less than or greater than. Well, the numbers I'm interested in are all smaller than 2. So my x value, whatever it is, has to be less than 2. As long as we have that, we are good. Okay, now for our next 2 problems. We are given things with a set operator in the middle. We have the same 2 regions discussed, okay? But this one has, this symbol is intersection. And it corresponds with the word and. So in this case, we are looking for the region that is in both this region and also in this region. So we'd be looking for overlap. This symbol is union, which corresponds with the word or. Now we have to be careful with this word or. Or in math is different from the English language or. In English, we have what we call an exclusive or. You hear this best in, for me, my mother was a disciplinarian, so I hear it in my mother's voice. If your dad was the disciplinarian, your grandmother, whatever, you hear it in their voice. If my mother said, you could have cake or you can have ice cream, if I went and I got both, I was in trouble. In math, we have what we call an inclusive or. In English, we hear A or B, period. In math, we need to hear A or B or both. Okay, so in this case, well, up here, we're looking for their overlap. And here, this is going to pick up anything that is part of either one of them. Okay, now the easiest way to do these problems, and since I'm talking about the same 2 regions, I can do this only once and then use the picture to answer both. What I'm going to do is I'm going to do 2 number lines, and I'm going to put one right over another so that I can imagine pushing these together so I can easily see where they overlap. Now when I do that, I want to make sure that these numbers end up in order. So for this first one, I need -4 and I need 0. For the second one, I need a -2, and I don't want to put the -2 over here. I want to put it so that it would be between the -4 and the 0 if I push these 2 things together. And then the same thing with the 1. I want it over here because if I push them together, I want it to be on the other side of the 0. Okay? Now let's just graph these. These have parentheses. These have brackets. And for our first region, it would be shaded like this. For our second region, it's shaded like this. Okay, so since this is and we're looking for their overlap, imagine drawing a line through here to see where our graph would be double shaded. Just imagine pushing it together. The part where it is it's double shaded is between -2 and 0. Our 0 had parentheses by it. It still has parentheses here. Our -2 had a bracket. It has a bracket here. So the intersection of these 2 regions is between -2 inclusive and 0 non-inclusive. Now if we do the union, that picks up everything that's in either one of them. It doesn't matter which one. So as long as it's shaded at all, ever is part of the solution. Well, if I were to push these together, the parts that would be shaded would be from -4 up to 1. This part is double shaded, and that would be a problem with English language or the exclusive or, but it's not a problem with math or. So our answer is from -4. I should have graphed this one. Sorry. Our answer in interval notation and then graph. Do the same thing here from -4 up to 1. The -4 had parentheses, so this has parentheses. The 1 had a bracket, so this has a bracket. We shade between them. And then our answer in interval notation, we pull directly off this graph. It's going to be -4 with parentheses up to 1 with a bracket. Now, the more you do these problems, the less likely it is that you'll actually have to write this down every time. If you are very good with visualizing spaces in your head, you might not need to do this at all. It will happen with practice. I don't expect it to happen though, but if you're able to do this without drawing the pictures, that's perfectly okay. Okay, So let's talk about how to solve inequalities. We're always going to write our answer in interval notation, and then we're going to graph it. Our basic rules for solving these are the same as they are for solving an equation, with one major exception. If we divide by a negative number, if we multiply or divide by a negative number, we have to flip the sign around. That's it. We'll work some problems like that for sure. Okay, so let's solve this one. I want to get my x by itself, so I'm going to subtract 5 from both sides. That gives me 2x is less than, that's going to be 12. Okay, and now I need to divide both sides by 2, and 2 is a positive number, so I do not have to worry about flipping anything. And I end up with x is less than 6. Okay, so we're always going to have to answer in interval notation, and we're going to have to graph. Most people find it easier to do the graph first and then do interval notation. My math lab does this in 2 parts. It has you enter the interval notation, hit enter, and then do the graph. Since you're going to have to do these, have to do both for every single problem, I suggest just going ahead and doing the graph and then getting the interval notation, and then you just enter the answers in the order the computer wants it. Okay? So the number I must see on the graph is a 6. This has a less than, no equal to, so I know it's going to have parentheses, one direction or the other. Now I want to decide which side of this I need to shade. Okay? Some of you have been taught to always shade the direction that your sign points. That only works if your x is on the left, and your x is not always going to be on the left. So if I were you, I would not rely on that rule, okay? Wherever your x is, just imagine plugging numbers in here and we want it to be true, okay? If I plug in 0 here, 0 is less than 6, so it's true, okay? Well, on your number line, where would 0 be? Is it on this side or is it on this side? It's on this side. So since 0 worked here and 0 is on this side, I would shade this side. So parentheses here and then shade here. Okay? Now to do your interval notation, we always talk about our left-hand boundary and then our right-hand boundary. Since this runs off forever in the left-hand direction, that goes to negative infinity. We don't put our infinities on our graph, they're just understood to be off to the sides. So my left-hand boundary is a negative infinity, and infinities, whether positive or negative, always get parentheses, comma, our right-hand boundary is 6. Okay, so if I work this one, I have negative 5x is less than or equal to 30. What I need to do to get x by itself is I need to divide both sides by negative 5. And I'm allowed to do that, but when I do that, I have to flip this sign around. I tend to circle it as soon as I recognize that I need to do that, because I've learned throughout the years that if I don't, my brain sort of leaves me and I forget to do it. This gives me x, flip it around, is greater than or equal to negative 6. This says I'm going to have a bracket on my negative 6, one way or the other. That doesn't look like a bracket. Put a negative 6 here. I just need to decide which side to shade. Now my x values need to be larger than negative 6. Think of a number that is larger than negative 6. 0 is larger than negative 6. 100 is larger than negative 6. Which side of this have my bigger numbers? Over here. 0 is on this side of negative 6, so I would shade this side. It has a bracket on it, and then I shade to the right. Okay, and then for interval notation, my left-hand boundary is at negative 6, and it continues up forever or off to infinity. bracket. Okay,